something is humming in the dark between the stars. Not loudly, not even close to loudly. It is a thin, continuous electromagnetic tone, the kind a plasma wave instrument translates into sound, and it has been playing out there for longer than our solar system has existed, waiting for something to enter it and listen. On the 25th of August, 2012, at a distance of 121.6 astronomical units from the Sun, a machine the size of a small car became the first human-made object in history to cross into that medium and record what it found. The galactic cosmic ray count doubled, then kept rising. The solar wind, present every moment of the preceding 35 years, vanished in days. The magnetic field shifted, and the density of the surrounding plasma jumped 40 times higher than anything measured inside the boundary. Every planet you have ever heard of lies on the other side of that boundary. Every ocean, every living thing. For 3.5 decades before that crossing, no instrument had ever confirmed what existed beyond it. What exists there is not empty space. It is a measured environment, irradiated, magnetized, cold beyond any human reference. And it presses inward against the sun's bubble from every direction, at every moment, without pause. In this video, we will trace how that bubble forms, map what it holds back, and follow the only machines that have ever crossed it to the other side. If this is the kind of thing that keeps you up at night, subscribing takes 3 seconds and means more of it finds its way to you. Get comfortable. What we are about to describe is not speculation. It is the measured, confirmed, instrument-recorded nature of where we actually live and what surrounds us on every side. There is a machine out there right now, tumbling through absolute darkness, more than 15 billion miles from the nearest star. It weighs roughly 800 kilograms, about the same as a small family car. Its main communications antenna is 3.7 meters across. The body of the spacecraft is compact, roughly the dimensions of a large dining table, but long booms extend outward in several directions. One carrying magnetometers sensitive enough to detect fields a fraction of a nanotesla in strength. One carrying the radioisotope thermoelectric generators that keep the machine alive. One carrying the science instruments that have been measuring the environment around the spacecraft for nearly 5 decades. Bolted to the outside of the main bus, facing the void, is a 12-inch gold-plated copper disc engraved with sounds and images from Earth, music, greetings in 55 languages, the sound of wind and rain, a human heartbeat, diagrams showing the position of our solar system relative to 14 pulsars, a cosmic address designed to remain valid for hundreds of millions of years. This machine is Voyager 1. It was built in the early 1970s using components that, by the standards of the present day, are almost bewilderingly simple. The onboard computing systems have less raw processing power than a modern digital wristwatch. The total memory capacity is measured in kilobytes. The entire electrical output of its 3 power generators, 3 radioisotope thermoelectric generators, converting the heat of decaying plutonium into electricity, has now fallen to around 220 watts. That is roughly the same as running 3 old-fashioned incandescent light bulbs. Everything Voyager 1 has ever discovered, every measurement it has ever transmitted, every piece of data it has ever returned across the void, was accomplished with this. Voyager 1 launched on the 5th of September 1977 from Cape Canaveral, Florida, carried into space by a Titan IIIe Centaur rocket. The mission it was designed for was 5 years long. It was built to reach Jupiter and Saturn, study those planets and their moons, and return its findings before its power gave out. It photographed Jupiter's Great Red Spot in detail that had never been possible from Earth. It discovered active volcanoes on Jupiter's moon Io, the first active volcanoes ever observed on any world beyond Earth. It studied the extraordinary complexity of Saturn's ring system and made the first close observations of the thick orange atmosphere of Saturn's moon Titan. Then the planetary mission ended, the encounters were complete, and instead of the spacecraft shutting down, it simply kept going. There was nothing to stop it. The gravitational assist from Saturn had flung Voyager 1 upward out of the plane of the solar system at approximately 17 kilometers per second. No engine fired to slow it. No signal redirected it toward a new target. It followed the trajectory that physics had prescribed and continued outward, second by second, month by month, year by year, into regions of space where nothing human had ever been. Today, Voyager 1 is at approximately 163 astronomical units from the Sun. 1 astronomical unit is the average distance between the Earth and the Sun, roughly 150 million kilometers. To understand what 163 of those units actually means, consider light. Light travels at approximately 300,000 kilometers per second, the fastest speed at which information of any kind can move. From the Sun to the Earth, light takes about 8 minutes. From the Sun to Voyager 1, that same light takes more than 22 hours. A signal sent from the Jet Propulsion Laboratory in California arrives at the spacecraft nearly a full day after transmission. The response takes another day to return. A single exchange, a single question and answer, requires almost 2 days of waiting each time. At its current speed of 17 kilometers per second, Voyager 1 could cross the entire width of the continental United States, roughly 4,500 kilometers, in about 4.5 minutes. That velocity, which would have represented an almost unimaginable achievement at any previous point in human history, is essentially nothing against the scale of the spaces that surround us. The nearest star system beyond our own, the Alpha Centauri system, lies approximately 4.3 light-years away. At 17 kilometers per second, reaching it would require more than 73,000 years of uninterrupted travel. Voyager 2, the twin, launched 16 days earlier than its sibling, on the 20th of August, 1977, but on a slower, more ambitious path that carried it past all 4 of the outer planets. It completed the only full grand tour of Jupiter, Saturn, Uranus, and Neptune in history, a sequence of flybys that will not be repeated on such a trajectory for another century and a half. After Neptune, Voyager 2 continued outward as well, angled southward relative to the plane of the solar system, following its own separate heading into the dark. It now sits at approximately 137 astronomical units from the Sun. These 2 machines are the most distant human-made objects in existence. No other spacecraft is even close. 2 machines, 2 directions, 2 independent instrument suites returning data from somewhere no instrument had ever been. What those instruments found, and what it means for our understanding of where we live, is the subject of everything that follows. But to grasp it, we first need to dismantle a misconception that has followed these missions through every decade of their existence. Because when journalists declared that Voyager 1 had left the solar system, they were using a phrase that, measured against actual science, is importantly wrong. And correcting it turns out to be not a minor point of terminology, but the entire hinge on which the story turns. The solar system is not a small thing. When most people picture it, they picture the Sun at the center, 8 planets in their orbits, and then empty space beyond Neptune. But this picture leaves out a structure of almost incomprehensible scale that the Sun's gravity still dominates. A structure so vast that Voyager, for all its decades of travel, has not even come close to entering it. The Oort cloud is the solar system's true outer structure, in any gravitational sense of that phrase. It is not a disk or a flat belt of objects like the Kuiper belt. It is a roughly spherical shell, enormous and diffuse, containing trillions of icy bodies. Dormant comets, most of them, bound to the Sun by gravity so feeble that the gentle tug of a passing star can dislodge them and send them falling inward on journeys that take thousands of years. The inner edge of the Oort cloud is thought to begin at somewhere around 2,000 astronomical units from the Sun. The outer edge is believed to extend to perhaps 100,000 astronomical units, approaching 1.5 light-years, where solar gravity fades to the point that the gravity of neighboring stars begins to compete with it. Voyager 1 is currently at 163 astronomical units. It has not reached the inner edge of the Oort cloud. At its current speed, arriving there would take approximately 300 years. Passing through the cloud entirely and emerging on the far side would take something in the region of 30,000 years. By any gravitational definition of the solar system's boundary, Voyager is still inside it, and will remain so for a period longer than recorded human civilization has existed many times over. So what did it actually cross? It crossed the heliopause. And the distinction between the heliopause and the edge of the solar system is not a technical footnote. It is the precise location where the science lives. The heliosphere is the region of space controlled not by the sun's gravity, but by the sun's wind. Gravity weakens with distance in a smooth and gradual way, extending outward without a sharp edge. The solar wind, the continuous stream of charged particles flowing from the sun's outer atmosphere at hundreds of kilometers per second, extends only as far as its outward pressure can overcome the inward pressure of the material between the stars. Where those two pressures reach equilibrium, a boundary forms. That boundary is the heliopause. And beyond the heliopause, the sun's electromagnetic influence simply ends. The particles it sends out no longer reach there. The magnetic field it shapes no longer governs the local environment. Whatever exists on that side of the boundary operates under entirely different rules, set not by our star, but by the broader galaxy. Before the Voyagers, this boundary was entirely theoretical. We knew the solar wind existed. We knew the interstellar medium, the thin gas, dust, and magnetic fields that fill the space between stars, also existed. We could build models of the interaction between them and predict roughly where the boundary should lie. But no instrument had ever been there. No direct measurement of any kind had ever been made. The nature of the transition, the character of the environment beyond it, the precise conditions that exist in the space between stellar systems, all of this was genuinely unknown. The two earlier deep space probes, Pioneer 10 and Pioneer 11, went into the outer solar system ahead of the Voyagers, but could not provide this data. Pioneer 10 sent its last detectable signal in January of 2003. Pioneer 11 had gone silent in September of 1995. Both are still moving outward, still following their trajectories into the dark, but they are inert. Their instruments are dead. They carry no data and return nothing. They are metal objects drifting through space with no voice left to speak. New Horizons, the spacecraft that flew past Pluto in 2015 and later visited a small, ancient object in the outer Kuiper belt, is active and heading outward. But it currently sits at around 60 astronomical units, far short of the first of the three boundaries that define the heliosphere's outer structure. It will be decades before New Horizons reaches the region where the Voyagers made their defining measurements, and its instrument suite was designed for a different kind of science. The measurements the Voyagers were built to make, particles, magnetic fields, plasma density, plasma oscillations, were precisely the measurements needed to characterize the heliopause and the medium beyond it. Only the Voyagers could do it, and what they found there was something no model, no simulation, no theoretical framework had fully anticipated. To understand what the Voyagers crossed, you have to understand what built it. And that means starting not at the edge of the solar system, but at its center, with a star that cannot stop exhaling. Every second of every day, without interruption, without pause, without any mechanism that could switch it off, the sun is losing mass. Not slowly and not gently. 4 million tons of matter are converted into pure energy every single second through nuclear fusion in the solar core. Hydrogen nuclei fusing into helium, releasing the energy that lights the Earth and warms everything alive on it. 4 million tons per second. The number is so large it barely registers. But that is not the mass loss that built the heliosphere. There is a second process, separate from fusion, that sends actual physical matter streaming away from the sun at extraordinary speed. Roughly 1.5 million tons of material departs the sun's surface every second, not as energy, but as particles, protons, electrons, and heavier ions physically ejected from the sun's outermost atmosphere and flung outward in every direction at once without stopping, at speeds ranging from 300 to 800 kilometers per second. This is the solar wind, and the heliosphere exists because of it. To understand where the solar wind comes from, you have to look at the sun's corona, its outermost atmospheric layer, and confront one of the most genuinely puzzling problems in all of solar physics. The surface of the sun, the layer we call the photosphere, has a temperature of approximately 5,800 Kelvin. The corona, which lies above it and extends outward into space, reaches temperatures of more than 1 million Kelvin. In some particularly active regions, it climbs to tens of millions of Kelvin. Think carefully about what this means. As you move away from a heat source, you expect the temperature to drop. Stand close to a fire and you are warm. Step back 10 meters and you are cooler. But the sun works in reverse. Step away from the photosphere, move outward through the chromosphere and into the corona, and the temperature does not fall. It rises by a factor of more than 100. The corona is over 170 times hotter than the surface below it. This is the coronal heating problem, and it has occupied solar physicists for nearly a century without a fully satisfying resolution. The most prominent proposed explanation was put forward in 1988 by Eugene Parker, the American physicist who had already changed the field with his 1958 prediction of the solar wind. Parker proposed that the corona is heated by an enormous number of tiny, impulsive events he called nanoflares. In this picture, the constant churning motion of the photosphere below the corona drags and shuffles the magnetic field lines threading through the coronal plasma, twisting and braiding them continuously. When neighboring field lines reach a critical angle of misalignment, they reconnect, snapping into a lower energy configuration and releasing a burst of energy into the surrounding plasma. Each individual event is tiny, barely detectable, but trillions of these events occur every second across the entire corona, and Parker argued that their combined output could account for the corona's extraordinary temperature. A competing explanation points to magnetohydrodynamic waves, Alfvén waves specifically, propagating upward from the turbulent interior of the sun, carrying energy into the corona and depositing it there through processes of resonant absorption and wave damping. Both mechanisms may well contribute, the question of which dominates under which conditions remains genuinely open. The Parker Solar Probe, which launched in August of 2018 and became the first spacecraft ever named after a living scientist — Parker was in the audience when the naming was announced — is now making measurements in the corona itself, diving closer to the sun than any previous mission, and its data is gradually illuminating what previous instruments could only observe from a distance. But the consequence of the corona's temperature, whatever its cause, is settled. At 1 million degrees and above, the thermal energy of the particles in the outermost corona exceeds the sun's gravitational binding energy at that altitude. In simpler terms, the corona is so hot that the sun cannot hold on to it. Material at those temperatures moves too fast to be captured by gravity. It escapes. Not occasionally, not intermittently, not in bursts during active periods, continuously. Every moment, the corona boils away into space in a supersonic flow of ionized plasma that spreads outward through the solar system in every direction. This is the solar wind, and once you understand the corona, its existence becomes not a discovery, but an inevitability. The wind is not uniform. It emerges faster from regions of the solar surface called coronal holes, places where the sun's magnetic field opens directly into space and allows material to accelerate freely outward along open field lines. From these regions, the wind can exceed 700 kilometers per second. From regions where the magnetic field forms closed loops that trap plasma temporarily before releasing it, the wind emerges more slowly, averaging around 300 to 400 kilometers per second. At any given moment, the solar system is threaded by these different streams moving at different speeds, creating a complex, structured wind with its own internal boundaries and interaction regions. The wind carries something else with it as it departs. Charged plasma moving through a magnetic field is governed by laws of electromagnetism that keep the two locked together. The magnetic field is, in the technical phrase, frozen into the plasma. So as the solar wind streams outward, it carries the sun's own magnetic field with it, dragging field lines out from the solar surface and stretching them through the solar system. This is where Eugene Parker's 1958 insight becomes architectural in its implications. The sun does not stand still relative to the wind it produces. It rotates, once every 27 days at its equator, slightly slower at its poles. As the wind streams radially outward and the sun turns beneath it, the field lines it carries are wound into a vast spiral pattern. Picture a garden sprinkler rotating and spraying water outward in all directions. The streams of water do not extend radially like spokes of a wheel, but curve outward in arcs, each arc the record of the sprinkler's rotation written into the pattern of the water. The sun does this with magnetic field lines, on a scale that spans the entire solar system. This is the Parker spiral, predicted by Parker in his original 1958 paper and confirmed 4 years later when NASA's Mariner 2 spacecraft, on its way to Venus in 1962, detected the solar wind directly and measured the orientation of the interplanetary magnetic field. The confirmation arrived quickly enough that Parker was still early in his career. He had proposed something the scientific community had initially refused to believe, and within 4 years, a spacecraft had flown through the evidence. The Parker spiral does not fade out at the orbits of the inner planets. It extends outward through the entire solar system. Every planet, every asteroid, every comet, every grain of interplanetary dust exists inside this spiraling magnetic web. The structure rotates with the sun, creating a vast, warped surface called the heliospheric current sheet, a boundary that winds through the solar system like the skirt of a ballerina, separating regions where the magnetic field points inward toward the sun from regions where it points outward. Every time Earth passes through this current sheet as it orbits the sun, the local space environment changes character. Fast and slow wind streams do not travel outward without interacting. Where a fast stream catches up to a slower one ahead of it, the plasma piles up and compresses, forming structures called co-rotating interaction regions, boundaries within the solar wind that are themselves sources of energetic particles and complex magnetic behavior. The solar wind, by the time it reaches the outer planets, is not the clean, steady flow it was when it left the corona. It is turbulent, structured, and layered. By the time it reaches Neptune's distance, the density has fallen by a factor of nearly 900 compared to its density at Earth's orbit. It is extraordinarily thin, but it is not nothing, and that distinction matters more than almost anything else in this story. And it is this wind, complex, spiraling, magnetized, continuous, thinning across the vast distances of the outer solar system, but never fully stopping until something stops it, that inflates the heliosphere. The solar wind pushes outward in all directions, and wherever it pushes, it carves out a region of space dominated by the sun's plasma and the sun's magnetic field. That region is the heliosphere. Its outer boundary, where the wind's pressure finally meets the equal and opposing pressure of the interstellar medium, is the heliopause. And everything alive, everything ever built, every planet and moon and asteroid and comet that has ever existed in the history of this solar system has existed inside it. The heliosphere breathes. During periods of high solar activity, solar maximum, which recurs on an 11-year cycle, the wind strengthens, the magnetic field intensifies, and the heliosphere expands outward slightly. During solar minimum, when the sun is quieter, the wind weakens and the heliosphere contracts. This 11-year rhythm is not merely theoretical, it is measurable in the cosmic ray flux reaching the inner solar system, in the radiation environment at Earth, and in the particle data the Voyagers have been transmitting for decades. The heliosphere is alive to the sun's mood in ways that only became fully clear once we could measure it from the outside. The scale of what the sun builds is easy to underestimate. From the photosphere to the heliopause is approximately 120 astronomical units, roughly 12 times further than the distance from the Sun to Neptune, the outermost of the 8 planets. Neptune, which feels remote enough to most people that a mission to reach it took 12 years, sits at about 30 astronomical units from the Sun. The heliosphere extends 4 times further in every direction. It is not a shell around the inner solar system. It is the solar system's atmosphere, enormous, dynamic, and, as we are about to see, indispensable. The solar wind does not slow down as it crosses the solar system. It thins, its density falling as it spreads across an ever larger volume, but its speed holds. From the moment it leaves the corona to the moment it reaches the outer reaches of the solar system, it continues outward supersonically, faster than the speed at which pressure disturbances can propagate through the surrounding medium. This is not merely a technical description. It matters enormously because it determines what happens when the wind finally meets the wall. At some distance from the Sun, the outward pressure of the solar wind becomes comparable to the inward pressure of the interstellar medium, the gas and magnetic field pushing back from outside. When 2 supersonic fluids meet a pressure boundary, they cannot simply flow through. They do not decelerate gently. They slam into a shock. The wind abruptly transitions from supersonic to subsonic speed across a boundary so sharp it qualifies, in the physical sense, as a discontinuity. This is the termination shock, the innermost of the heliosphere's 3 outer boundaries, and the first one the voyagers crossed. The physics of a shock transition of this kind are violent in a specific way. The kinetic energy of the fast-moving plasma has to go somewhere when the speed drops. It converts into thermal energy. The plasma behind the shock, the plasma that has just been abruptly decelerated, heats dramatically as the kinetic energy of motion becomes the energy of random particle movement. Temperatures in the post-shock region can exceed 100,000 Kelvin. The wind does not stop at the termination shock. It slows, compresses, and heats. Then it continues outward in a new state, slower, hotter, denser, and increasingly turbulent, into the region beyond. Voyager 1 crossed the termination shock in December of 2004, at a distance of approximately 94 astronomical units from the Sun. Voyager 2 crossed it in August of 2007, at approximately 84 astronomical units. The 10 astronomical unit difference between them was not a measurement error or an inconsistency. It was a discovery. The heliosphere is not a sphere. The solar system is not stationary in the galaxy. It orbits the galactic center at approximately 230 kilometers per second, and this motion means the solar system is constantly plowing into the surrounding interstellar medium from one direction. The side of the heliosphere facing into that flow, the upwind side, the nose, is compressed by the ram pressure of the incoming interstellar material. The downwind side, the tail, is stretched out behind, comet-like, trailing in the direction the solar system has come from. Voyager 1, heading upward and northward out of the plane of the planets, crossed the termination shock closer to the nose of this asymmetric structure. Voyager 2, heading southward, crossed further in on the flank. The different distances confirmed what models had predicted in principle, but never directly verified. The heliosphere's shape reflects its motion through the galaxy, and that shape is distinctly not round. The particle instruments aboard both spacecraft track the crossing through a population of particles that only exists inside the heliosphere. Neutral atoms from the interstellar medium are not deflected by magnetic fields. Because they carry no charge, they pass through the heliopause and drift inward until solar ultraviolet radiation strips them of their electrons, ionizing them. Once ionized, these atoms are captured by the solar wind's magnetic field and swept along, eventually reaching the termination shock, where the turbulent conditions there accelerate them to high energies. The resulting population, energetic particles of interstellar origin that have been accelerated by heliospheric physics, are called anomalous cosmic rays, and Stamatios Crimigis and the particle instrument teams aboard both Voyagers use them as tracers to pin down the shock crossings precisely. The flux of anomalous cosmic rays changes sharply at the termination shock, and that change is written clearly in the data. Beyond the termination shock lies the heliosheath, the thick, churning buffer zone between the inner heliosphere and the heliopause. It is not a thin membrane. It is a region that, at the distances the Voyagers crossed it, extends roughly 30 to 50 astronomical units further outward. In the heliosheath, the decelerated solar wind piles up. The plasma grows denser and hotter. The magnetic field, no longer being stretched outward by a fast-moving wind, begins to fold and compress. The outward pressure that has sustained the heliosphere for billions of years slowly dissipates, and the inner push of the interstellar medium steadily asserts itself. By the time the plasma reaches the heliopause, it has exhausted its momentum. The solar wind's last act is to press against the boundary it created, and the boundary holds, barely, dynamically, continuously, against everything the galaxy pushes back with. The heliosheath turned out to be stranger than almost any pre-crossing model had anticipated. What the Voyagers found when they passed through it would complicate the picture considerably. But that strangeness was only the opening chapter of a longer surprise. The real revelations came when the spacecraft reached what lay beyond it. The heliosheath belongs to neither world. It is not the inner solar system, where the solar wind flows fast and the sun's magnetic field governs everything. It is not interstellar space, where the galaxy sets the rules. It is the territory in between, thick, turbulent, and stranger than theorists had bargained for. And both Voyagers spent years crossing it before either of them reached the heliopause. The models had imagined it as relatively orderly. The decelerated solar wind would compress and flow around the sides of the heliosphere in structured fashion, eventually pressing outward against the heliopause. The reality was considerably messier. The magnetic field in the heliosheath did not behave as expected. Rather than lying in smooth, ordered sheets, it folded back on itself. Field lines coiled and reconnected, and the Voyagers detected magnetic bubbles, closed, roughly spherical magnetic structures each about 1 astronomical unit in diameter, strung together like foam, where the models had predicted nothing of the kind. This was not a minor deviation from the predicted pattern. It was a fundamentally different magnetic topology. The heliosheath, it turned out, is not a buffer zone in any gentle or passive sense. It is a region where the solar wind's magnetic field is actively being reorganized by its encounter with the boundary ahead. The plasma in the heliosheath behaved strangely too, and the two spacecraft did not see the same thing. Voyager 1, on its northward heading toward the nose of the heliosphere, encountered a region where the plasma almost stopped moving altogether. The solar wind had decelerated not just from supersonic to subsonic, but almost to a standstill. A stagnation zone roughly 8.5 astronomical units wide where the plasma sat, compressed and hot, pressing against the approaching boundary. No model had predicted anything like it. Voyager 2, crossing through a different part of the heliosphere on its southward heading, encountered nothing comparable. It passed through a more orderly transition, a broad slowing region, then a sharper boundary layer before the heliopause. The difference between the two spacecraft's experiences revealed that the heliosheath is not uniform. Its structure varies around the heliosphere depending on direction, solar activity, and local geometry. Just inside the heliopause, Voyager 2 discovered something else that had been predicted by models, but not previously confirmed by direct measurement: a magnetic barrier. This is a region where the solar magnetic field, compressed as the decelerating plasma piles up against the heliopause from inside, builds in intensity, a wall of strengthened solar field stacked against the boundary. This barrier is not merely a curiosity. It acts as an additional partial filter on the galactic cosmic rays trying to enter the heliosphere from outside. Some fraction of the incoming cosmic rays are turned back or scattered by this compressed field before they can penetrate inward. The heliosphere's protection, in other words, does not operate solely at the heliopause. It has depth, and something happens on the other side of the heliopause that adds another layer to this picture. Neutral hydrogen atoms from the interstellar medium, atoms that carry no electrical charge and are therefore not deflected by magnetic fields, can flow straight through the heliopause. Most of the interstellar medium's charged particles are kept out, but neutral atoms pass through freely. As these neutral hydrogen atoms flow inward from outside, they do not simply enter without effect. Where they press against the outer face of the heliopause, the interaction between the outward-flowing heliospheric plasma and the inward-flowing neutral atoms causes a pileup, a region of increased neutral hydrogen density just beyond the heliopause, compressed by the stalling of the flow. This structure, called the hydrogen wall, was first detected in the early 1990s through its signature in ultraviolet light, the particular wavelength emitted when hydrogen atoms absorb and re-emit sunlight. The two Voyager spacecraft detected this ultraviolet signature. New Horizons confirmed and extended the measurement from beyond Pluto in 2018. The neutral atoms that managed to push through the heliopause and enter the heliosphere proper also carry information. Once inside, they encounter solar ultraviolet radiation and the outgoing solar wind. The radiation strips them of their electrons, ionizing them. Now charged, they are swept up by the solar wind's magnetic field and become part of the solar wind's own plasma population, carried outward as what are called pickup ions, particles of interstellar origin that have been absorbed into the sun's own wind. These pickup ions carry the chemical fingerprints of the interstellar medium, and measuring them from inside the heliosphere has proven to be one of the more unexpected ways to study the environment beyond the boundary. Those measurements recently yielded a significant revision. In 2023, observations made by New Horizons from approximately 50 astronomical units, deep in the outer solar system but still well inside the heliosphere, suggested that the local interstellar medium contains roughly 40% more neutral hydrogen than several widely used prior estimates had assumed. That finding matters because the pressure the interstellar medium exerts on the heliosphere depends partly on how much hydrogen it carries. A denser interstellar medium presses harder. A harder press means the heliosphere is under more constraint than was previously calculated. The boundary is closer, the geometry more compressed, and the dynamics of the interaction between the two media more vigorous than the older models suggested. All of this, the foamy magnetic field, the stagnation of the plasma, the magnetic barrier, the hydrogen wall, the infiltrating neutral atoms, was happening in the border zone that both Voyagers had to cross before they reached the heliopause itself. They crossed it for years. And then, after years, something changed. In the summer of 2012, something Voyager 1 had been measuring continuously for 35 years suddenly stopped. But there was a problem, a significant one. The single most definitive marker of a heliopause crossing is a sharp jump in the density of the surrounding plasma, from the thin, hot, decelerated solar wind of the heliosheath to the denser, colder plasma of the interstellar medium. Every model agreed on this. The density contrast at the boundary was expected to be large and unmistakable. The instrument that could measure this directly, Voyager 1's plasma science experiment, had failed in 1980, 32 years before the crossing. The spacecraft had no functioning tool to directly sample the plasma density of its surroundings. Without that measurement, the case for a heliopause crossing, no matter how suggestive the particle data, could not be closed. Then the magnetic field data complicated things further. Leonard Berlage, the magnetometer scientist at NASA's Goddard Space Flight Center, who had been tracking Voyager 1's magnetic field measurements for decades, found that the field direction across the boundary crossings remained essentially unchanged. The models had predicted that crossing the heliopause should produce a rotation in the magnetic field vector, a clear pivot from the solar field orientation to the galactic field orientation. No such rotation appeared. The direction was stable, close to the Parker spiral angle that had characterized the field throughout the heliosheath. Some researchers argued this meant Voyager had not crossed the heliopause at all, but had entered some new and unexpected transition region, a structure nobody had named yet, a magnetic highway or a depletion zone, something between heliosphere and interstellar space that previous models had not anticipated. The debate played out through the second half of 2012 and into 2013. The particle data said one thing: the magnetic field data said something else. And without a working plasma instrument, there was no obvious way to resolve it. Don Gurnett, the plasma wave scientist at the University of Iowa, who led the team responsible for Voyager 1's plasma wave subsystem, knew there was an indirect route to a plasma density measurement, but it required patience and a degree of luck. His instrument measures electromagnetic oscillations in the surrounding plasma. Plasma oscillates naturally at a frequency determined by its electron density. Higher density, higher frequency. If something energetic enough disturbed the plasma around the spacecraft, it would set it ringing at this characteristic frequency, and the instrument would detect it. But in the quiet of the outer heliosheath and interstellar space, nothing was providing that disturbance reliably. The instrument needed the sun to cooperate. In the spring of 2013, it did. A large burst of solar activity, a coronal mass ejection that had erupted from the sun months earlier, sent a powerful shockwave racing outward through the solar system. By the time that shockwave reached Voyager 1's location, more than 120 astronomical units from the sun, it had been traveling for roughly a year. When it arrived, it drove the plasma around the spacecraft into oscillation. Gurnett's instrument detected the signal clearly. The oscillation frequency corresponded to an electron density of approximately 0.08 electrons per cubic centimeter, roughly 40 times denser than the plasma of the outer heliosheath, and entirely consistent with the values expected in the interstellar medium. The measurement was decisive. Gurnett described the moment of realization as taking about 10 seconds. The density put Voyager 1 unambiguously in interstellar plasma. Working backward through the data, the team pinpointed when the spacecraft had crossed the heliopause, around the 25th of August, 2012, at a distance of 121.6 astronomical units from the Sun. The announcement came in September of 2013 at a press conference where Ed Stone, physicist at Caltech and Voyager project scientist since 1975, declared that Voyager 1 had crossed into interstellar space. It had been there, silently, for 13 months before anyone on Earth could be certain. The machine, built with 1970s technology, designed for a 5-year mission, running on less power than a set of light bulbs, had become the first human instrument to touch the medium between the stars. And what it found there had only just begun to be understood. Once the crossing was confirmed, the full picture of what Voyager 1 had been measuring on the other side of the heliopause came into focus. Each instrument told a different part of the same story, and together they produced something no theoretical model had been able to provide. A direct measurement of what the space between stars is actually like. Start with the particles. Voyager 1 carries 2 instruments capable of detecting energetic charged particles. Together, they function as a continuous census of the particle environment around the spacecraft, counting how many particles of various types and energies pass through in any given time. Inside the heliosphere, that census had been dominated for 35 years by particles of solar origin. Anomalous cosmic rays accelerated at the termination shock, energetic ions from solar activity, the various products of the Sun's ongoing influence on its surrounding plasma. The anomalous cosmic rays, as described, vanished at the crossing. But what replaced them was not simply an absence, it was a population of a fundamentally different character. Galactic cosmic rays are particles originating from sources scattered throughout the Milky Way, supernova remnants, neutron stars, binary systems, and at the highest energies, processes in other galaxies entirely. They have been bouncing through the galactic magnetic field for timescales reaching millions of years, and by the time they arrive at any location in interstellar space, their directional information has been almost entirely scrambled. They come from everywhere at once. Beyond the heliopause, Voyager 1's particle instruments recorded their flux climbing to levels 2 to 3 times higher than the maximum values ever observed inside the heliosphere during the deepest solar minimum. That elevated baseline is what interstellar space delivers, continuously, regardless of what the Sun is doing. The increase was not uniform across all particle energies. For galactic cosmic rays in the lower energy range, below roughly 200 million electron volts per nucleon, the jump was far more dramatic. These lower energy particles are the ones the heliosphere blocks most effectively. Inside the heliospheric bubble, even during solar minimum, their flux is suppressed by factors of 5 to 10 compared to interstellar values. They had been present throughout Voyager 1's journey, only in trace amounts. Beyond the heliopause, they appeared in abundance for the first time. The character of the radiation environment shifted, not just in quantity, but in the specific population of particles, toward a regime that the heliosphere had been quietly filtering out for the entire duration of the mission. Now turn to the magnetic field. The field did not vanish at the heliopause. This was perhaps the single most important finding to come from the magnetometer data, and the one that had initially confused the interpretation of the crossing. The interstellar medium carries its own magnetic field, a galactic field generated and sustained by currents flowing through plasma across the Milky Way, shaped by supernova shockwaves and the motion of gas and stars over millions and billions of years. This field has a strength in the local interstellar medium of roughly 0.3 to 0.5 nanotesla. Voyager 1 measured the transition from the solar field in the outer helio sheath, which had weakened to around 0.2 nanotesla, to the galactic field outside, which measured around 0.4 to 0.5 nanotesla. The field actually strengthened across the heliopause. It did not disappear or weaken. It changed identity. The direction of the field also changed, but not sharply and not immediately. The models had predicted a clean rotation in the field vector at the heliopause, a pivot from the solar field orientation to the galactic. What the magnetometer recorded instead was a gradual rotation playing out over days to weeks. The solar and galactic fields blended across a transition layer of finite thickness, a zone of mixed magnetic character rather than a knife-edge boundary. This is what the magnetic field data, so puzzling in the months after the crossing, was actually revealing. That the heliopause is not a mathematical surface, but a region, one where two vast magnetic systems intermingle before one gives way entirely to the other. Between the energetic events driven by solar activity, something else was detectable. Don Garnett's plasma wave instrument registered a persistent, faint, low-frequency electromagnetic oscillation in the surrounding medium, a continuous signal at roughly 2 to 3 kHz. Plasma oscillates naturally at a frequency set by its electron density, and this quiet, constant tone was the interstellar medium sounding its own note, encoding its density in an electromagnetic signal that had been playing in the dark between the stars for as long as that plasma had existed in its current state. When NASA released an audio rendering of this signal in 2013, converting the electromagnetic oscillations into the range of human hearing, the result was a thin, almost glassy sound, faint and continuous, rising and falling slightly as the density around the spacecraft varied, not a sound wave in any conventional sense. The interstellar medium is far too thin to transmit mechanical pressure. What Garnett's instrument detected were oscillations in the electric field of the plasma, translated into audio as a tool for human comprehension. The tone was real, the underlying physics was real, and it continued. The interstellar medium in the immediate vicinity of the heliopause is not calm or static. The magnetic field measurements showed fluctuations in both strength and direction on timescales of hours to days. Turbulence driven by shock waves from distant supernovae, by the motion of interstellar clouds through the local medium, and by magnetohydrodynamic instabilities inherent to any conducting fluid threaded by a magnetic field. The space between the stars hums and churns at its own rhythm. Voyager 1 was the first instrument ever placed within it, and it was listening. 6 years passed. Voyager 1 was alone in interstellar space, listening, measuring, transmitting its findings back across a distance that grew by another billion miles every few months. Then, on the 5th of November, 2018, Voyager 2 joined it. The crossing happened at approximately 119 astronomical units from the Sun, 3 astronomical units closer to the Sun than Voyager 1's crossing in 2012 on the southern flank of the heliosphere rather than the northern, through a part of the heliopause that had never been sampled before. Two spacecraft, two directions, two independent crossings of the same boundary, separated by 6 years. The scientific value of that combination was enormous, but it was one specific difference between the two crossings that transformed everything. Voyager 2's plasma science instrument was working. The instrument on Voyager 1 that directly measured the properties of the surrounding plasma, its speed, density, temperature, and flow direction, had failed in 1980, long before the heliopause crossing, before the termination shock crossing, before the spacecraft had even reached the Kuiper belt. For 32 years of the most important part of its journey, Voyager 1 had been flying blind in this one crucial respect, forced to infer plasma conditions indirectly from magnetic field behavior and the occasional plasma oscillation triggered by a solar event. Voyager 2's equivalent instrument had survived. John Richardson, the principal investigator for the plasma science experiment at the Massachusetts Institute of Technology, had been waiting decades for this moment. What his instrument recorded at the heliopause was unambiguous and almost instantaneous. On one side of the boundary, the plasma was solar wind, decelerated and heated by its long journey through the heliosheath, but still flowing outward, still moving at roughly 100 to 150 kilometers per second in the radial direction, still consisting predominantly of solar material. At the heliopause, this flow stopped. The transition took less than 1 day to complete. The solar wind plasma simply disappeared, and in its place the instrument found something it had never measured before: a denser, hotter, and essentially stationary plasma of interstellar origin. The density of the interstellar plasma beyond the heliopause, measured by Voyager 2, was approximately 0.05 to 0.06 electrons per cubic centimeter. By any terrestrial standard, this is an extraordinarily thin medium. Earth's atmosphere at sea level contains around 25 quintillion particles per cubic centimeter, and even the best laboratory vacuum contains billions. But compared to the plasma of the outer heliosheath, which runs at roughly 1,000th of a particle per cubic centimeter, the interstellar medium at the crossing was 20 to 40 times denser. The density jump that the models had always predicted as the defining signature of the heliopause was there, exactly as expected, measured directly for the first time. The temperature of the interstellar plasma recorded by Voyager 2 was approximately 30,000 to 50,000 Kelvin, high by the standards of the heliosheath plasma the spacecraft had just departed, and far above the temperatures of the dense gas clouds that fill the galactic disk. This requires careful interpretation. Temperature in plasma physics refers to the average kinetic energy of individual particles, not to the macroscopic sensation of heat that a human body would experience. A plasma at 50,000 Kelvin in the interstellar medium contains particles moving at tens of kilometers per second, but so few of them exist in any given volume that the total energy they could transfer to a macroscopic object is negligible. You could pass your hand through it and feel nothing at all. The medium is hot in the particle physics sense and cold in any practical sense simultaneously. The distinction matters for understanding the physics, even if it is counterintuitive. Comparing the two crossings produced a composite portrait of the heliopause that neither spacecraft could have provided alone. Voyager 2 encountered a thinner and simpler heliopause structure than Voyager 1 had. The magnetic transition, from solar field orientation to galactic, was sharper. The interstellar magnetic field beyond the boundary was stronger. There was no stagnation region of the kind that had confused Voyager 1's approach. The heliopause crossed by Voyager 2 resembled a cleaner, more defined boundary, more like the knife edge the models had originally imagined. These differences are not contradictions. They are evidence that the heliopause surface is not uniform. It varies in character depending on where you cross it, when you cross it, and what conditions prevailed on both sides at that particular moment and location. What the two crossings together established is something that had been assumed but never proven. The heliopause is a real, definable, physical boundary. It has consistent gross properties: a density jump, a shift in particle populations, a change in magnetic field domain. that appear at both crossing points despite the separation in time, distance, and direction. And it has variable fine-scale structure that reflects the complex, dynamic nature of the interaction between two vast and turbulent fluid systems pressing against each other across a surface spanning billions of kilometers. Both spacecraft now move deeper into what scientists call the very local interstellar medium, the region immediately surrounding the heliosphere, which is still partially influenced by the heliosphere's presence and therefore not quite representative of the pristine galactic medium further out. True interstellar space, undisturbed by any trace of the Sun's influence, lies further still. But what the Voyagers have sampled is close enough to reveal what the barrier they crossed was actually holding back. The heliosphere holds something back. The question is, what? And Voyager's direct measurements in interstellar space provide the answer in numbers rather than estimates. Galactic cosmic rays are not radiation in the sense that most people understand that word. They are not electromagnetic waves like radio signals, visible light, X-rays, or gamma rays. They are physical particles, mostly protons, but also helium nuclei, carbon, oxygen, silicon, iron, and other heavier atomic nuclei, along with electrons, moving through the galaxy at velocities that approach the speed of light. They originate from the most energetic processes the Milky Way produces. Supernova remnants are the primary factory. When a massive star explodes at the end of its life, the expanding shell of gas and magnetic field that results can persist for thousands of years, sweeping outward through the interstellar medium and continuously accelerating charged particles trapped in the turbulence at its leading edge. Each time a particle bounces back and forth across this shock front, it gains energy. Over thousands of years, this process, called diffusive shock acceleration, builds particle energies across an enormous range, from modest to extraordinary. Pulsars contribute their own accelerated particles. Binary star systems, where one compact object strips material from a companion, generate their own shocks and magnetic environments capable of particle acceleration. And at the grandest scales, the jets of plasma launched by actively accreting black holes at the centers of distant galaxies produce particles energetic enough to travel across millions of light-years of intergalactic space before reaching the Milky Way. The energy range spanned by galactic cosmic rays is among the widest of any natural phenomenon in physics. At the low end, they carry energies of a few million electron volts, comparable to the particles produced in medical radiation equipment. At the high end, the most energetic cosmic rays ever measured carry energies exceeding 100 billion electron volts concentrated in a single subatomic particle. To grasp what that means in everyday terms, a proton at that energy carries the same kinetic energy as a professionally thrown baseball, compressed into an object smaller than an atomic nucleus and moving at a speed indistinguishable from the speed of light. The heliosphere does not block cosmic rays by acting as a physical wall. Charged particles in a magnetic field do not travel in straight lines, they curve. The tighter the radius of their curvature relative to the scale of the magnetic structures they encounter, the more effectively those structures can scatter, redirect, and turn them back. Inside the heliosphere, the solar wind's embedded magnetic field creates a vast, turbulent, continuously renewed magnetic environment that acts on incoming galactic cosmic rays throughout their entire inward journey. Lower energy cosmic rays, with smaller momentum and correspondingly smaller radii of curvature in the interplanetary magnetic field, are scattered the most aggressively. Many are reflected back outward before they penetrate anywhere near the inner solar system. Higher energy cosmic rays, with greater momentum and larger radii of curvature, are harder to deflect and penetrate more deeply, but even they are partially moderated by the journey through the heliosphere's magnetic structure. The quantified result of this shielding, now anchored by Voyager's direct measurements of the cosmic ray flux in interstellar space for comparison, is significant. The heliosphere reduces the galactic cosmic ray flux reaching the inner solar system by approximately 70 to 75% compared to the unshielded interstellar value. For lower energy cosmic rays, those below roughly 1 billion electron volts per nucleon, the suppression is more dramatic still, reaching factors of 5 to 10. Only the most energetic cosmic rays, above roughly 10 billion electron volts, pass through the heliosphere with relatively little attenuation. This shielding is not a minor effect. It is the difference between a radiation environment that permits complex chemistry and biological evolution, and one that systematically degrades them. The solar cycle modulates the shielding continuously. During solar maximum, when the sun's wind is stronger and the interplanetary magnetic field is more disordered, more incoming cosmic rays are scattered and the flux in the inner solar system drops. During solar minimum, when the wind weakens and the field becomes more orderly, more penetrate. This 11-year oscillation has been tracked continuously for over 70 years by networks of ground-based neutron monitors, detectors that register the secondary particles produced when cosmic rays strike Earth's atmosphere, and by spacecraft throughout the solar system. It is one of the most reliably measured phenomena in heliospheric science. The biological stakes of this shielding are not abstract. Galactic cosmic ray, heavy ions, iron nuclei, silicon nuclei, and similar particles moving at substantial fractions of the speed of light interact with biological tissue in ways that are qualitatively different from the lower energy radiation that dominates inside the heliosphere. When one of these particles passes through a living cell, it does not simply ionize a few atoms along its path. It can shatter the nucleus of any atom it strikes, generating a spray of secondary particles, neutrons, protons, pions, and heavier fragments that spread damage across a wide radius. The resulting injury to genetic material involves clustered lesions, multiple simultaneous breaks in the double strand of the DNA molecule in the same small region, damage that is far more difficult for the cell's repair mechanisms to address than isolated, single-strand breaks from lower energy radiation. The heliosphere reduces the frequency at which this kind of damage is delivered to every living organism on Earth. It has been doing so for as long as life has existed here. Consider what this means for human spaceflight beyond the heliosphere. Astronauts aboard the International Space Station, which orbits within Earth's magnetosphere and therefore within 2 layers of electromagnetic protection, already receive a radiation dose roughly 10 times higher than the average person on Earth's surface. That exposure is carefully tracked and limited by mission duration. A crew traveling beyond the heliopause would face the full, unmoderated galactic cosmic ray flux that Voyager's instruments have directly measured, an environment with none of the heliosphere's filtering and none of Earth's magnetosphere. The cumulative radiation dose over a decades-long transit would substantially exceed the career exposure limits currently imposed by every major space agency, with elevated risks of cancer, cardiovascular damage, and effects on the central nervous system, including potential cognitive decline. These are not speculative consequences extrapolated from theory. They are direct projections from measured particle fluxes, applied through well-established radiobiology. The interstellar medium is not merely vast. It is actively hazardous to the biology of any species that evolved inside a stellar bubble. The protection extends beyond biology and beyond Earth. Earth itself is triple shielded in a way that most living things simply take for granted. The heliosphere is the outer layer, vast, electromagnetic, suppressing roughly 3/4 of the galactic cosmic ray flux before anything reaches the inner solar system. Earth's own magnetosphere is the second layer, a region of space around the planet shaped by Earth's internal magnetic field, deflecting most of the charged particles that survive the heliosphere's filter. The atmosphere is the third, an enormous column of gas, effectively equivalent to 10 meters of water in shielding depth, that absorbs the energy of particles that make it through both outer layers. The 3 systems are not perfectly independent. During geomagnetic storms, when the magnetosphere is disturbed by energetic solar events, cosmic ray access to the upper atmosphere increases temporarily. But under normal conditions, the combination keeps the cosmic ray dose at sea level to a manageable fraction of what bare interstellar space would deliver. Mars offers a stark illustration of what happens when most of this protection is absent. The red planet has no global magnetic field. The dynamo that once drove it through Mars's molten interior cooled and solidified billions of years ago, leaving only localized remnant patches of crustal magnetism that provide no planet-scale shielding. Its atmosphere is less than 1% as dense as Earth's at the surface, absorbing only a fraction of the cosmic ray flux that reaches it. Under those conditions, any subsurface water ice that might exist on Mars is exposed to a radiation environment that drives radiolysis, the chemical breakdown of water by radiation, at a higher rate than Earth's subsurface water ice experiences. The surface chemistry of Mars is shaped partly by this radiation, producing oxidizing compounds that make the top layers of its soil hostile to organic molecules. The heliosphere does not make Mars habitable. Its absent atmosphere and distance from the Sun are also deeply relevant, but it reduces the radiation burden on whatever might exist beneath the surface by a margin that matters for astrobiology. The icy moons of the outer solar system present their own version of this question. Europa, Enceladus, and Titan all carry geological and chemical evidence suggesting liquid water beneath their ice shells, environments where the chemical conditions for life might in principle persist. These worlds exist within the heliosphere, but at distances where the heliospheric shielding is already reduced. The solar wind is thinner, the interplanetary magnetic field weaker, the cosmic ray flux higher than at Earth's orbit. Under a significantly smaller or absent heliosphere, the radiation environment at their ice surfaces would intensify further. The chemistry occurring in the ice shells, the depth to which radiation-driven processes penetrate, the stability of organic molecules near the ice-water interface, all of these would shift. The heliosphere's protective history stretches back further than any instrument has directly measured. Galactic cosmic rays striking Earth's upper atmosphere produce cosmogenic isotopes, beryllium-10 and carbon-14 among them, at rates that vary with the cosmic ray flux reaching the atmosphere. The abundance of these isotopes preserved in ice cores, ocean sediments, and tree rings provides a proxy record of past cosmic ray flux at Earth, and therefore a record of how the heliosphere's shielding has varied over time. These archives stretch back tens of thousands of years for ice cores and further in certain marine sediments, showing the signature of the solar cycle clearly, along with longer-term variations that reflect changes in both solar output and the geomagnetic field. The heliosphere's protection is not a constant. It has fluctuated through history, and those fluctuations are written into the geology of the planet it has been sheltering all along. The size of the heliosphere is not a fixed constant. It is an equilibrium, the product of a balance between two opposing pressures, one pushing outward and one pushing inward. Change either pressure and the heliopause moves. The heliosphere expands when the solar wind is stronger. It contracts when the solar wind weakens. And it contracts still further when the interstellar medium pressing against it from the outside becomes denser. That second variable, the density and character of the interstellar medium surrounding the solar system, has changed substantially over the history of the solar system. It will change again, and the consequences of those changes are written into the rock and ice of Earth itself. At this moment, the solar system is embedded in a structure called the local interstellar cloud. It is a warm, partially ionized region of gas, approximately 30 light-years across, with a density of roughly 1/10 to 3/10 of a particle per cubic centimeter and a temperature of somewhere between 6,000 and 8,000 Kelvin. This is the specific medium that the Voyagers measured just beyond the heliopause. It is what currently sets the external pressure against which the solar wind must push, and it is therefore what determines how large the heliosphere is today. The solar system will not remain inside the local interstellar cloud indefinitely. Based on the cloud's velocity relative to the Sun and the solar system's trajectory through the galaxy, the exit could come within a few thousand to tens of thousands of years. What exists on the other side of the cloud boundary is not known with certainty. Some models suggest the solar system will enter a lower density region, part of the broader structure called the local bubble, where the external pressure on the heliosphere would decrease and the heliopause would expand outward. Others suggest the solar system may encounter denser patches. the uncertainty is real, and its implications are significant. The local bubble itself deserves a moment. It is the larger structure within which both the Sun and the local interstellar cloud currently reside. A vast, irregular cavity in the interstellar medium, approximately 1,000 light-years across, whose interior is far less dense than the average interstellar medium of the Milky Way. The cavity was carved by a series of supernova explosions, roughly 15 of them based on current modeling, beginning approximately 14 million years ago, originating from massive stars in a stellar association that has since moved on. Each explosion sent a shockwave expanding outward into the surrounding gas, sweeping material ahead of it and leaving behind a thinned-out interior. The solar system entered this cavity around 5 million years ago. Before that, it was in denser interstellar material. Since entering the local bubble, it has been traveling through a relatively benign galactic neighborhood, sparse, warm gas that exerts relatively little pressure on the heliosphere. This matters because it means the heliosphere we observe today, the one the Voyagers have mapped and measured, is larger and more protective than it might have been at other points in the solar system's history, or than it will necessarily be in the future. The local interstellar cloud is denser than the average interior of the local bubble, but it is still orders of magnitude less dense than some structures in the galactic disk. While the solar system lives within the local bubble, the heliosphere is relatively large. When it eventually leaves, the conditions it encounters may be very different. The geological record preserves evidence that those conditions have changed significantly in the past. In the ocean floor, in ferromanganese crusts that grow layer by layer at rates of millimeters per million years, and in sediment cores extracted from the Atlantic, Pacific, and Indian Oceans, scientists have found something that should not exist in any measurable quantity on Earth: iron-60. This is a radioactive isotope of iron produced in supernova explosions, not by any process that occurs naturally on Earth's surface. It has a half-life of 2.6 million years, which means any iron-60 present when the solar system formed 4.5 billion years ago would have decayed away billions of years before now. Iron-60 found in Earth's geological record must have arrived from outside, carried by interstellar dust from relatively recent supernova explosions in the solar neighborhood, drifting through the interstellar medium and settling onto the ocean floor. Anton Wallner, a nuclear physicist at the Australian National University, led a series of studies extracting and measuring iron-60 from sediment cores taken from multiple ocean basins. His work, published from 2016 onward, confirmed that the iron-60 signal is global and coherent, not a local anomaly, but a worldwide deposition event of interstellar origin. It shows distinct peaks around 2.5 million years ago, and again around 6 to 8.5 million years ago. Both peaks correspond to epochs when the solar system appears to have traversed regions of enhanced interstellar material. Debris from relatively nearby supernova explosions that temporarily increased the density of the local interstellar medium. And a denser interstellar medium means higher external pressure on the heliosphere. Higher external pressure means a compressed heliopause. A compressed heliopause means reduced shielding. More galactic cosmic rays reaching the inner solar system. More radiation at every planetary surface inside the bubble. The iron-60 record is the fingerprint of those events. It is the interstellar medium's own signature, written in atoms that cannot have come from anywhere else, preserved in the sediments of an ocean that was not even thinking about them. Then, there is what appears to have happened approximately 2 million years ago, and what happened then is the kind of discovery that changes the way you think about your planet's history. In June of 2024, astrophysicist Merav Ofer of Boston University published a paper in the journal Nature Astronomy that represented, in her own words, the first quantitative demonstration that an encounter between the solar system and something outside it could have physically affected Earth's climate. The study, which used sophisticated computer models, validated against data from the Gaia satellite, the European Space Agency mission that has produced the most detailed three-dimensional map of stars in the galaxy ever assembled, traced the trajectory of the solar system approximately 2 to 3 million years into the past, and mapped against it the position of a structure called the local ribbon of cold clouds. The ribbon is a system of large, dense, very cold clouds composed primarily of hydrogen atoms. Cold, dense clouds of this kind are fundamentally different from the diffuse interstellar material of the local bubble interior. They are 4 to 5 orders of magnitude denser, thousands of times denser or more. A single such cloud carries enough mass to exert an entirely different level of pressure on anything it encounters. OFA's models identified one cloud in particular, located in the constellation Lynx and called the local Lynx of Cold Cloud, whose trajectory may have intersected with the solar system's path around 2 to 3 million years ago. What her simulations showed is difficult to describe without sitting with it for a moment. When the models were run with the solar system passing through this cold, dense cloud, the external pressure on the heliosphere increased so dramatically that the heliopause was compressed to approximately 0.22 astronomical units from the Sun. The Earth's orbit lies at 1 astronomical unit. The heliopause, in this scenario, was pushed inside Earth's orbit. Every planet in the solar system, Earth, Mars, Jupiter, Saturn, and all the rest, was outside the heliosphere. They were in direct contact with the interstellar medium. The supporting evidence for this encounter is the isotopic record. Measurements of iron-60 in deep-sea sediments, Antarctic snow, and lunar samples cluster around a deposition peak dating to between 1.7 and 3.2 million years ago. Plutonium-244, another isotope produced in supernova explosions and also found in the same sediment layers, shows a matching signal. These are atoms of interstellar origin, delivered directly to Earth's surface during a period that OFA's models identify as the time of the cloud encounter. If the heliosphere was compressed inside Earth's orbit, there would have been no electromagnetic barrier to prevent interstellar material from reaching Earth's surface and the Moon. The isotopic record would look exactly like it does. It is a plausible mechanism operating through known physics. OFA and her collaborators were careful about what they claimed. The probability of the specific encounter they modeled is low. The geometry of the solar system's past trajectory has significant uncertainty. The timing of the cloud passage overlaps with the glaciation onset rather than preceding it precisely. This is a physically coherent hypothesis supported by converging evidence from isotopic records, computer simulations, and galactic cartography. It is not a proven event, but it is not speculation either. It is the best current reading of data that, taken together, points in a specific direction. That direction is this: the heliosphere is not merely a feature of the solar system, it is infrastructure. And the geological record of Earth carries the marks of at least one occasion when that infrastructure came close to failing. The heliosphere we observe today is the product of a particular moment in the solar system's much longer journey. Step back far enough and the picture becomes stranger still. The Sun orbits the center of the Milky Way at approximately 230 kilometers per second. A single complete orbit, one circuit of the galactic center, takes approximately 230 million years. The Sun has completed this circuit roughly 20 times since it formed, 4.5 billion years ago. Each orbit is not a simple loop through identical conditions. The galaxy is not uniform. It has structure, dense spiral arms where star formation is concentrated, where supernova rates are higher, and the interstellar medium is compressed and turbulent, and quieter interarm regions, where the medium is calmer and less dense. The solar system passes through these different galactic environments continuously, spending tens of millions of years in each. And as the conditions outside the heliosphere change, the heliosphere responds. During passages through the dense inner regions of spiral arms, the interstellar medium pressing against the heliosphere is more turbulent and, at times, denser. Nearby supernovae occur more frequently. Shock waves from those explosions ripple through the local medium, episodically increasing its density and the pressure it exerts on the heliospheric boundary. The heliopause moves inward during such epochs. Galactic cosmic rays penetrate further into the inner solar system. The radiation environment at every planetary surface changes. The geological and biological record of Earth extends across several such galactic passages, though the evidence is diluted and complicated by the many other processes operating simultaneously over hundreds of millions of years. Connecting specific galactic passages to specific events in the geological record is genuinely difficult, and claims of direct causation must be made with care. What the physics firmly establishes is the direction of the effect. The heliosphere breathes in time with the galactic environment it moves through, expanding during quiet interarm passages and contracting during more turbulent encounters. The heliosphere we inhabit today, large, relatively stable, sitting inside the quiet interior of the local bubble, is not the heliosphere the solar system has always had. It is one configuration among many that have existed across deep time. These long timescale variations are beyond direct measurement. We cannot send instruments across millions of years of galactic history, but there is a different class of variation, shorter in timescale, larger in immediate detectability, that a mission called the Interstellar Boundary Explorer has been documenting in unprecedented detail since 2009. The Interstellar Boundary Explorer, known as IBEX, is a small spacecraft the size of a bus tire. Launched in October of 2008, it occupies a high orbit around Earth from which it images the heliosphere's boundaries using a technique that the Voyagers, with their point-by-point in situ measurements, cannot replicate. Rather than flying through the boundary and measuring what is immediately around it, IBEX detects energetic neutral atoms, particles that originate when charged particles in the heliosheath, or just beyond the heliopause, undergo a charge exchange with neutral atoms and become neutral themselves. Because neutral atoms travel in straight lines unaffected by magnetic fields, they carry directional information. By detecting them at Earth's location and tracing their trajectories back to their origins, IBEX builds maps of the regions where they were created. Effectively, it images the heliosphere's outer boundary from the inside. In its first full-sky map, released in 2009, IBEX found something that had not been predicted by any model: a narrow, roughly circular arc of enhanced energetic neutral atom flux crossing the sky at the front of the heliosphere, a bright diagonal stripe that came to be called the IBEX ribbon. Nothing in the theoretical literature had anticipated it. It was a significant, organized feature at the very boundary the models had been trying to describe for decades, and it appeared from nowhere. The leading explanation that has emerged from years of subsequent analysis involves a chain of charge exchange processes extending beyond the heliopause. Neutral solar wind atoms that travel outward past the heliopause are eventually ionized by the local interstellar medium and captured into the interstellar magnetic field as pickup ions. These ions subsequently undergo another charge exchange, becoming neutral again and traveling back inward, where IBEX detects them. The ribbon appears at the specific arc of sky directions where the local interstellar magnetic field is oriented perpendicular to the line of sight from the Sun, the geometry that makes the charge exchange chain most efficient for particles returning inward. 11 years of IBEX observations have progressively supported this secondary energetic neutral atom model, and the data pattern across a full solar cycle is consistent with it. But the details of the process, how exactly the pickup ions behave in the local interstellar medium before returning, how the magnetic field turbulence affects the efficiency of the chain, remain areas of active investigation. IBEX also addressed a question that the Voyager crossings had raised but could not resolve: the shape of the heliosphere. The Voyagers provided 2 data points on the heliopause surface. IBEX provided a global picture. The data, accumulated across more than a decade, reveals an asymmetric structure, not a sphere, but something elongated, with the Sun positioned closer to the upwind face and the heliosphere extending significantly further in the downwind direction, trailing behind the solar system's motion through the galaxy. David McComas, the principal investigator for the IBEX mission at Princeton University, described the overall shape as something like a comet, with a substantial heliotail extending downwind. Merav Ofer's competing model, derived from magnetohydrodynamic simulations that assign a larger role to magnetic pressure in shaping the heliosheath, produces a structure with two large lobes, a shape she described as resembling a croissant, rather than a smooth, elongated tail. Both models remain consistent with the available observational data, which as yet cannot fully distinguish between them. IBEX also tracked the heliosphere's response to a multi-year period of reduced solar wind output. Between 2009 and 2014, the solar wind was unusually weak, weaker than at any time in the previous 5 decades of spacecraft observation. The heliosphere contracted during this period. Then the solar wind recovered and the heliosphere expanded again. IBEX measured the consequences of these changes at the heliospheric boundaries and found that the boundary's response lagged the solar wind change by 2 to 3 years. The time it takes for the altered wind conditions to propagate outward to the heliopause and for the resulting changes to propagate back inward as energetic neutral atoms. The heliosphere is not a rigid structure. It breathes with the sun's breath, and IBEX has now watched it do so across a full solar cycle. These are extraordinary observations, but they are still remote sensing. IBEX sees the boundary from inside the heliosphere, inferring conditions at the boundary from particles that have made the outward journey and returned. The Voyagers experienced the boundary directly, and what both missions independently revealed is how much remains unknown about the structure the solar system lives in, and how much more precisely those unknowns need to be constrained. That is what the Interstellar Mapping and Acceleration Probe is now doing. IMAP launched on the 24th of September 2025 aboard a SpaceX Falcon 9 rocket from the Kennedy Space Center in Florida. It reached its operational orbit at the first Lagrange point, a gravitationally stable position approximately 1 million miles from Earth toward the Sun, on the 10th of January 2026, and began its 2-year primary science mission on the 1st of February 2026. It carries 10 scientific instruments and was built and is operated by the Johns Hopkins University Applied Physics Laboratory. David McComas, who led IBEX, leads IMAP as well. The step up in capability from IBEX is substantial. IMAP's energetic neutral atom detectors provide approximately 15 to 35 times greater sensitivity than IBEX, depending on the energy range being measured. Not a modest improvement, but an order of magnitude advance in the precision with which the heliosphere's boundaries can be mapped. The energy range covered is wider, and the angular resolution of the maps produced is finer. Where IBEX revealed the existence of the ribbon and established its basic properties, IMAP is designed to characterize its origin, to determine which specific physical process, operating in which specific location, produces the ribbon's distinctive pattern. This remains one of the most important unresolved problems in heliospheric physics. IMAP also simultaneously measures conditions in the inner solar system, the solar wind's composition, the energetic particles accelerating within the heliosphere, the characteristics of the interstellar neutral atoms that flow inward past the heliopause, and it transmits near real-time data on solar wind and energetic particle conditions from its Lagrange 1 vantage point, providing approximately 30 minutes advance warning of potentially hazardous solar events heading toward Earth, a practical application of heliospheric science with immediate consequences for the safety of satellites, power grids, and astronauts in orbit. The arc from Voyager to IBEX to IMAP spans nearly 50 years. 2 spacecraft designed in the 1970s flew blind into the unknown and returned measurements nobody had the tools to anticipate. A small spacecraft the size of a bus tire spent 11 years imaging the boundary remotely and discovered things no model had predicted. And now a mission purpose-built to answer the questions those discoveries raised is operational at Lagrange Point 1, mapping the heliosphere with a precision that would have seemed impossible when the Voyagers launched. Each step revealed how much the previous step had left unseen. The question is what IMAP will reveal that we are not yet imagining. While IMAP builds its maps and the next generation of heliospheric science begins, The machines that started all of this are running out of time. Voyager 1 and Voyager 2 are powered by radioisotope thermoelectric generators, devices that convert the heat produced by the radioactive decay of plutonium-238 into electricity. Each spacecraft launched with 3 of these generators. The physics that governs them is implacable. Plutonium-238 decays at a rate set by its half-life of approximately 87.7 years, releasing heat as it does so. The generators convert that heat into electrical current through an array of thermocouples, junctions between 2 different materials that produce a voltage when one side is hotter than the other. At launch in 1977, each spacecraft's 3 generators together produced approximately 470 watts of electrical power. That number has been falling ever since, by approximately 4 watts per year, because each year there is slightly less plutonium left and slightly less heat to convert. By early 2025, each spacecraft was generating somewhere around 220 watts, less than half the launch output after nearly 5 decades. The trend continues. Every year, 4 more watts disappear from the budget, and the engineers responsible for the mission must decide what to turn off. The cameras went first in 1990. There was no scientific justification for keeping them running in the featureless dark beyond the planetary system, and turning them off freed power for the instruments that mattered. Heaters followed, components that kept electronics and fuel lines warm enough to function. Each time a heater was deactivated, the engineering team accepted a calculated risk that the affected system would survive the deep cold of interstellar space without protection. Some of those gambles are still paying off nearly 30 years later. Science instruments have been retired one by one across the decades. Those measuring physical properties less relevant to the interstellar mission deactivated first to preserve power for the fields and particles instruments that return the most valuable data from beyond the heliopause. In early 2025, the decisions became visibly sharper. On the 25th of February, NASA's engineers powered down Voyager 1's cosmic ray subsystem, the set of 3 telescopes that had been measuring the flux and energy of cosmic ray particles since the spacecraft launched. It had survived nearly 48 years in space and completed its scientific purpose. Cutting it freed enough power to extend the remaining instruments' operational lives. On the 24th of March, the equivalent instrument on Voyager 2, its low-energy charged particle detector, was switched off as well. After those shutdowns, each spacecraft was operating with 3 active science instruments. Further deactivations are planned for 2026 and beyond. The engineering team's best projection is that at least 1 science instrument on each spacecraft may remain operational into the 1930s, though 48-year-old hardware in interstellar space offers no guarantees. Keeping the instruments running requires keeping the spacecraft in contact with Earth. This is itself an achievement that deserves to be held carefully in mind. Voyager 1's transmitter outputs approximately 22 watts. The power budget for all communication, a signal sent from a 12-foot dish antenna pointed as precisely as aging thrusters can manage toward a planet more than 15 billion miles away. The signal leaves the spacecraft and travels at the speed of light. It takes approximately 22 to 23 hours to arrive at Earth. The round-trip time for a command and response now exceeds 45 hours. An instruction sent from the Jet Propulsion Laboratory in California on a Monday afternoon does not reach the spacecraft until Tuesday, and the spacecraft's acknowledgement does not arrive until Thursday. By the time Voyager 1's signal reaches Earth's surface, it has spread across a sphere whose radius is 15 billion miles. The power of that signal has fallen to a fraction of a trillionth of a watt, extracted from the thermal noise of the electronics in the receiving dish itself. The NASA Deep Space Network, 3 complexes of large parabolic antennas at Goldstone in California, near Canberra in Australia, and outside Madrid in Spain, receives and processes these signals. The 70-meter dishes at those facilities retrieve data, arriving at approximately 160 bits per second. That is slower than the earliest dial-up internet connections from the 1990s. It is the bandwidth through which humanity's only active presence in interstellar space reports everything it knows. Suzanne Dodd, the Voyager project manager at the Jet Propulsion Laboratory, has described the mission as one that refuses to end. The spacecraft have outlasted the careers of the engineers who built them and 3 generations of mission controllers. Every year the team wakes up expecting the unexpected, because at the age these machines have reached, anything that goes wrong is likely to be something that has never happened before. There will come a moment, somewhere in the years ahead, when the power can no longer sustain the last remaining science instrument. The measurements will stop. Then, at some point further out, the transmitter itself will fall silent, not abruptly, but gradually, as the power available to run it falls below the threshold needed to generate a detectable signal. The Deep Space Network will stop hearing Voyager 1 and Voyager 2, and the spacecraft will continue on their trajectories regardless, carried by the same momentum that has driven them outward for nearly half a century, moving into the interstellar medium at 17 kilometers per second, silent and alone. The objects themselves will outlast their voices by a very long time. Voyager 1 will pass within approximately 1.5 light-years of a star called Gliese 445 in the constellation Camelopardalis in approximately 40,000 years. It will not slow down. It will not stop. It will pass through that star's neighborhood and continue outward into the galaxy, still carrying its magnetometers and its science boom and its golden record. The record whose surface is already being slowly eroded by the same galactic cosmic rays that Voyager's instruments measured and reported. Whatever message it was meant to carry will eventually be unreadable, but for now, it is still sending. The data is still arriving. The measurements are still being made. Take the measurements the Voyagers made, the particle flux, the magnetic field strength, the plasma density, the temperature, and ask what they mean for anything that might try to cross that environment, rather than merely pass through it briefly as a machine with no crew, no fuel requirement beyond its decaying plutonium, and no deadline. The answer that comes back from the data is unsparing. Galactic cosmic rays arrive from every direction continuously. They do not come in waves that can be timed and avoided. They do not have a season or a quiet period. The flux that Voyager's instruments recorded beyond the heliopause is simply the permanent condition of the interstellar medium, elevated by a factor of 2 to 3 above the maximum values ever measured inside the solar system with the low energy component, the particles most efficiently blocked by the heliosphere, present at 5 to 10 times the flux that exists inside the protective bubble. Any object placed in this environment is immersed in it, from every direction, without interruption, for as long as it remains there. For a spacecraft carrying people, this is not an abstract concern. It is the first and most fundamental engineering constraint. And the physics of shielding against galactic cosmic rays is cruel in a specific and counterintuitive way. Conventional metal shielding, aluminium, steel, lead, works well against the electromagnetic radiation and lower energy charge particles that dominate the inner solar system. Against galactic cosmic rays, particularly the heavy ions, it fails in a way that initially makes no sense. When a high-energy cosmic ray nucleus strikes an atom of shielding material, the collision produces secondary particles, fragments of the impacted nucleus, neutrons, pions, and other products, that can themselves cause damage. Below a certain thickness of shielding, adding more material reduces the number of primary particles reaching the interior. But above that threshold, the secondary cascade produced inside the shield becomes more damaging than the original cosmic ray would have been unshielded. More metal means more dose, not less. The shield becomes a particle multiplier. Materials with a high hydrogen content behave better. Hydrogen nuclei are close in mass to the incoming protons that constitute most cosmic rays, and a proton colliding with a hydrogen nucleus deposits its energy more efficiently and produces fewer heavy secondary fragments. Polyethylene, water, and liquid hydrogen have all been studied as shielding candidates for this reason. The best estimates suggest that optimized hydrogen-rich shielding could reduce the galactic cosmic ray dose by somewhere between 30 and 50% compared to the unshielded value. This is a meaningful reduction. It is not enough. A crew in interstellar space for decades, even with the best passive shielding available, would accumulate radiation doses, far exceeding the career limits every space agency imposes on its astronauts. The cancer risk alone would be substantial, and the potential for central nervous system effects, cognitive changes, accelerated neurological aging, from the heavy ion component of the flux adds a dimension that passive shielding cannot address at all. Active magnetic shielding has been proposed. Superconducting coils generating a magnetic field around the spacecraft large and strong enough to deflect incoming cosmic rays before they reach the hull, mimicking what the heliosphere does on an enormous scale, but compressed around a single vehicle. The physics is coherent. The engineering is overwhelming. A field strong enough to deflect particles carrying billions of electron volts of energy would require coils of such size and mass, carrying currents of such magnitude, that the system would dominate the spacecraft's entire mass budget many times over. And it would need to operate continuously, without failure, without degradation, for the entire duration of a transit measured in decades. No superconducting system has ever been built to operate on such a timescale without maintenance. The energy problem compounds the shielding problem. Assume, for the sake of argument, that a future civilization solves the radiation challenge. They still need to get there, and they need to power everything for the journey. At 10% of the speed of light, a velocity roughly 2,000 times faster than Voyager 1, and requiring propulsion technology that does not exist in any form beyond theoretical proposals, the transit to Alpha Centauri would take approximately 43 years. Every joule of energy consumed during those 43 years, for propulsion, for life support, for the radiation shielding systems, for heating against the cold, must be carried from the departure point. There is no energy source in the interstellar medium. The particle density is too low for any ramscoop design to extract meaningful fuel at any plausible transit velocity. The magnetic field energy density is negligible. Solar panels are useless within years of departure. A nuclear fission reactor capable of sustained output over 4 decades would need to operate without human maintenance for a period more than twice as long as the oldest continuously running reactor ever built on Earth, in an environment of continuous radiation bombardment that exceeds anything any reactor has been designed to withstand. Then there is the thermal environment. Far from any star, a passive object radiates its thermal energy into space and equilibrates toward the temperature of the cosmic microwave background, approximately 2.7 Kelvin or 270 degrees below the freezing point of water. At that temperature, the lubricants in mechanical systems solidify. The electrolytes in battery systems freeze. Structural materials that are ductile and tough at room temperature become brittle. Electronic components designed for the temperature ranges inside the inner solar system cease to function. Maintaining any habitable or operational temperature requires continuous heating. Continuous heating requires continuous power. The power comes from the reactor. The reactor is already carrying the weight of everything else. Each of these challenges, taken individually, might be dismissed as an engineering problem awaiting a future solution. Taken together, they are something else. They are a description of the interstellar medium as an active, hostile environment, one that is not merely distant, but that specifically, systematically degrades any complex system that enters it. Distance can be overcome by patience or by speed. The properties of the medium cannot be engineered away. They are what the medium is. The heliosphere is not, it should be noted, unique to our star. Every star that generates a stellar wind inflates its own protective bubble, what astronomers call an astrosphere, around its planetary system. The same physics that produces the heliosphere operates around every main sequence star in the galaxy, modulated by the star's mass, age, activity, and the properties of the local interstellar medium it moves through. The astrospheres of some stars have been detected directly. Ultraviolet observations of nearby stars have revealed the signatures of hydrogen walls piling up at their heliopause equivalents, confirming that the physical structure we inhabit extends, in analogous form, to other stellar systems. But the range of astrospheres in the galaxy is enormous. Massive, hot, luminous stars produce powerful stellar winds and correspondingly large astrospheres that may extend hundreds of astronomical units. At the other end of the scale, red dwarf stars, small, cool, long-lived, and accounting for roughly 70% of all stars in the Milky Way, produce much weaker stellar winds. Their astrospheres are correspondingly smaller, sometimes dramatically so. For planets orbiting in the habitable zones of red dwarf stars, zones that lie very close to the star because red dwarfs are dim and their warmth reaches only a short distance, the margin between the astrosphere boundary and the planet can be thin. In some configurations, the habitable zone planet may sit near the edge of the astrosphere rather than deep inside it, with correspondingly reduced protection from galactic cosmic rays. A passing dense interstellar cloud, a period of reduced stellar output, a particularly turbulent stretch of local interstellar medium, any of these could temporarily compress the astrosphere inward past the habitable zone, exposing the planet to the full unshielded flux for years, decades, or longer. And the fraction of the galaxy's volume occupied by astrospheres, even accounting for all 200 to 400 billion stars in the Milky Way, is vanishingly small. Add up every stellar protective bubble of every star in the galaxy, and you arrive at a number that represents an extraordinarily small fraction of the galaxy's total volume. The remainder, the overwhelming majority of the Milky Way, measured by volume, is the interstellar medium. Irradiated, cold, magnetically turbulent, hostile to complex chemistry, hostile to biological tissue, hostile to engineered systems. This is the dominant state of the galaxy. Stars and their astrospheres are rare exceptions, isolated points of warmth and protection scattered across a wilderness that would destroy most of what life or technology requires to function. This is the galaxy as the Voyager measurements reveal it, not the luminous network of connected possibilities that human imagination tends to impose on the night sky. An archipelago, tens of billions of islands, each surrounded by its own thin bubble of stellar protection, each separated from its nearest neighbors by light years of the measured, documented, particle-counted medium that both Voyagers are now moving through. Which brings us, finally, to a question that physicists and philosophers have been wrestling with since the middle of the 20th century, and which the Voyager data now illuminates from a new angle. If the galaxy contains hundreds of billions of stars, many of them old enough to have allowed billions of years for life to develop, and if even a small fraction of planetary systems around those stars host living things that eventually develop technology, if all of that is true, where is everyone? Why is the sky silent? Why have we detected no unambiguous sign of another technological civilization in all the decades of searching? This is the Fermi paradox, named for the physicist Enrico Fermi, who posed the essential question informally in 1950. Many answers have been proposed. Perhaps the development of intelligence is extraordinarily rare, so rare that we may be alone in the observable universe despite the billions of candidate worlds. Perhaps technological civilizations tend to destroy themselves through warfare or environmental collapse or the misuse of their own tools before they can reach the stage of interstellar communication. Perhaps civilizations exist in abundance, but choose silence, or have chosen a form of existence we cannot recognize or detect. These are serious proposals, and none has been definitively ruled out. But the Voyager measurements offer a physically grounded contribution to this conversation that is different in character from any of those proposals. The interstellar medium is not merely a large distance to cross, it is an environment that actively degrades anything that enters it. Electromagnetic signals, radio waves, light, any form of electromagnetic radiation, cross it with relative ease, attenuated by distance, but not fundamentally impeded. Physical matter must survive it. That is a categorically different challenge. A galaxy in which signals travel freely, but physical matter cannot survive. The transit is a galaxy that looks exactly like ours from the inside. Civilizations could exist across thousands of light years, communicating through electromagnetic channels if they have learned to detect each other, while remaining physically unable to visit each other at all. The interstellar medium would be the ocean between their islands, too wide and too hostile for any vessel to cross. Each civilization trapped inside its astrosphere, looking out, hearing nothing coherent from the void, and unable to reach the source of anything it might detect. Whether this is the correct explanation for the Fermi paradox is unknown. The question of whether the interstellar medium constitutes an absolute barrier or merely a very difficult engineering challenge remains genuinely open. Future technologies, operating on principles we cannot now specify, might conceivably address the radiation, the energy, and the thermal problems in ways that are not currently apparent. Nothing in the physics rules it out permanently. But the Voyager data makes clear what must be addressed. The barrier is not the distance. It is the nature of what fills the distance, and that nature is now measured. We are not simply protected, we are conditionally protected. The heliosphere that shields this solar system is not a permanent feature of the universe, or even of the solar system's long history. It is a dynamic equilibrium between one star's continuous exhalation and the specific properties of the specific medium that star currently moves through. That equilibrium has shifted before, substantially, and will shift again. The geological record of Earth carries the evidence of at least one occasion when it shifted so far that the planets were exposed directly to the interstellar medium for a period that may have left its mark on the climate of a world already beginning to produce the genus that would eventually include us. The Sun will keep burning for approximately 5 billion more years. The heliosphere will persist in some form for as long as the Sun produces a wind. What the solar system encounters during those 5 billion years, what interstellar clouds it passes through, what supernova shockwaves reach it, how the local bubble evolves around it, will determine how large and effective the heliosphere is at any given moment. These are not small uncertainties. They are the variables on which the radiation environment of every planetary surface in this solar system depends. The Voyagers measured the environment on the other side of the heliosphere's boundary. That is the fact at the center of everything this story has described. And what those measurements reveal, when their implications are followed through with the same rigor that produced them, is that the space beyond our bubble is not the benign emptiness of popular imagination. It is not waiting to be explored by anyone willing to make the journey. It is a measured, characterized, physically demanding medium that imposes specific costs on anything that enters it, costs that no technology currently in existence is equipped to pay. We live inside a bubble. The bubble is maintained by a star. The star will not burn forever. And the interstellar medium, which has been waiting outside that bubble since before the solar system formed, will still be there when it is gone. That is what the measurements say. That is what the data means. And for as long as the Voyagers continue to transmit, for as long as the last instruments keep running and the last signal keeps arriving across 15 billion miles of dark, the measurement continues and the meaning deepens.